Hello and welcome back. In this video, I'm going to cover section 10.1, Points, Lines, and Planes from Contemporary Mathematics by OpenStax. The learning objectives for this section are identify and describe points, lines, and planes, express points and lines using proper notation, and determine union and intersection of sets. So points, lines, and planes. So points and lines were first defined by a mathematician named Euclid, and I'm going to highlight his name here. That's how you say that, Euclid. And he wrote that a point was that which has no part. In other words, it has no length, width, or depth, which he called breadth. He was, kind of ancient philosopher kind of deal. So, they talked all nice and length, width, and breadth. So, and here are two of the first five what we call postulates, as they are applicable to this first topic. So postulates are kind of this thing that we accept to be true, without really any proof or verification, because it just so naturally seems to be, all right? And that's kind of my best explanation. There's a more formal explanation out there. So postulate 1 says a straight line segment can be drawn joining any 2 points. Another way I like to say this is through any 2 points is exactly one line. So to illustrate postulate 1, if we drew 2 points, which we usually represent points this way, we can draw one line. And if we had another point, we could draw a line through that in that regard, like that. But 2 points contain one line. You can't draw another second line through those 2 given points. Otherwise, it's just going to be the exact same point. And then postulate 2 says any straight line segment can be extended indefinitely in a straight line. And so the idea is that, you've got these 2 points. If you connect them and they stop, that's a line segment. And then if it keeps going forever, which we denote by little arrows, then that is a line, and that goes on forever. All right, and so that's the idea of a line segment versus a straight line, and we'll talk about that. So those are postulates. They're kind of things that almost seem obvious, but in order to set a foundation, we give them what's called a postulate. We put them into words and call them a postulate. So here are the symbols. So math loves symbols. We love writing things in symbols. So here are the symbols for these things. So a point, which we have here, this point. Points are defined with capital letters. All right, so here is an example of a point. A point could really be anything, right? Oftentimes we write it as a filled-in circle, but it could be an asterisk, it could be a square, it could be a star, or I'm going to do a little pentagon because, but it could be a star, as I've drawn here, that asterisk-looking thing. It's the idea that it just represents somewhere in space, but that concept has no length, width, or height, or depth. And then we have a line segment. So that's this symbol here. This is a bar, so we say this is AB bar or bar AB. And a segment goes from point A to point B, and it includes the 2 points, which means that the lines are filled in, or the points are filled in. And then a ray is something that extends from, in this case, ray A to B, extends from A and goes to B, and it goes indefinitely in the right direction, literally the right. It goes to the right indefinitely. And then here we have ray BA, or AB, but this is going from B to A, so it is actually going in the left direction, as we see here. And then this, if we add 2 little arrows to the end of our bar symbol, then that is a line that goes off indefinitely, or to infinity, in both directions. So this would go forever in both directions. So this is interesting. This is called a half line. So you see now we have this little open circle here. All right, so we have this little open circle that my laser is pointing to, and then it's going to the right. So this is half line from A to B, but we do not include, that's the important part here, we do not include A in the direction of B. And so A is getting excluded in this case. All right, so we have an open circle here, A. B is included, and then it goes on forever. And then we have the same thing excluding B. So this is the ray going from B to A, or sorry, this is the half line. They call it a half line from B to A, not including point B in the direction of A. So these are just some basic symbols from geometry that we use. It's kind of like a shorthand. So we don't have to write all these words. We just write this symbol and we know what we're talking about. So let's look at each of these. And we want to define what each of these means. And then look at them on this figure 10.3. So starting here with number 1, this is line segment. This is a line segment. So this is line segment from D to E, and that includes D and E. So line segment from D to E, and we're including the endpoints. So that's right here on our figure. So that's that D to E line segment. All right, and then F, this is just point F. And so that would just be literally the point F just there on the figure. Now, number 3, this is line DF. So this is well, another way we would say this if we were defining it. So this is an indefinite line. And I would write it as passing through D and F. So this is an indefinite line passing through D and F. And then finally we have EF, and this is just a line segment from E, get it right in a minute, E to F, including E and F. So that would be what those definitions are, or kind of what those symbols define on each of those. EF line segment is right there on this graph. This whole thing is line DF. So if you're talking about like what points were included, so the points included in line segment DE, for example, let me get my little pointer here. So the line segment DE includes point D and point E. And then the point F just includes itself, F. The line DF includes the points D, E, and F. And then the line segment EF includes the points E and F. So that's kind of like how we include things as well. So lines can be kind of classified into 3 buckets. They can be parallel, which we'll talk about here. They can be perpendicular, or they're neither parallel nor perpendicular. You're either one or the other, or you're neither. All right. So parallel lines are lines that they exist in the same plane and move in the same direction and never intersect. That's the key thing about parallel lines, is that they are never intersecting. And we have a symbol for parallel lines. This is L1 and these double bars, L2 here, right? So L1 double bar, L2. And over here is an example of Let me get my laser pointer. Over here is an example of two parallel lines. They're kind of the same distance from each other, represented by these dotted lines with the D, and they are never going to touch each other. They're in the same plane of existence, and then they're going off forever indefinitely, and they will never touch. And so on the flip side, we have perpendicular lines down here. So we have perpendicular lines, and they do intersect at 90 degrees. So that's the special part about perpendiculars, is that they intersect at a 90-degree angle. So here we can see in this picture that we've got line L1 and we've got line L2, and they intersect at 90 degrees. They create a perfect 90-degree corner here. And of course, we do have a symbol for that, because that's one of math's favorite things, is symbols. And it's this little upside down T-looking thing that says that they're perpendicular. And if you kind of look, it comes from what perpendicular lines look like. If you go over here and highlight these two lines, right, then that looks like the symbol for perpendicular, because they're making perfectly right angles. So this next is kind of an interesting thing to include, but I'm going to talk about it. I'm going to go over some of these terms in here. So what we're talking about here is something called union and intersection of sets. So union, I want you to think about brings together. Intersection is just things that overlap. Okay, so to give you the short of it, we refer to the union of two or more sets containing all of the things in either set or elements. Okay, so union basically is bringing everything together, and we're not counting duplicates. So if there's duplicates, we just, they say, okay, well, that's a duplicate. We only need one thing to represent it. So union brings together. Intersection contains only the elements that are in common to each set. Okay, so union, which we use this kind of U-looking symbol, this very upright U, and then intersection, we use basically it's upside down. So U for union, if you think about it like that, but it's not a U, it's this special symbol that kind of looks like a capital U. And then if you turn that upside down, here we have the intersection symbol. So union and intersection. So let's look at an example. Looking at the union and intersection. So first we're going to look at the intersection of ray starting at B going to D, and the ray starting at A going to C. So I'm going to highlight. I'm going to get a we'll get this blue highlighter. And so B going to D is going to go this way. And then I'll get another color, C going to A. Okay, so C going to A. And so the question is, where do they overlap? So looking right in here, BC is where they overlap. So their union is going to be equal to basically line segment BC. All right, so let's clear that off. And let's look at the next one. So let's get our highlighter. So find the union this time. So the union of AB, AD. So AB is in this area. And then AD is all of this area. Now, union brings them together. It doesn't look at where they overlap. It says bring in everything. So everything in this case is going to be the line segment A to D. And that's going to bring in everything A, B, C, and D. All right, let's clear that off and look at the next one. So line AD with union BC. All right, so line AD, that's everything here. Union with BC. Now remember, union brings together everything. And so if you already have everything, then it is just everything. So this is just line AD. So because BC is inside of AD, right? BC is part of the line AD. AD is what we get when we union. It's everything in there. And then what about line AD with the intersection of BC? So AD, so again, that's everything. AD intersecting with BC. So that is just where they overlap. So the overlap is just going to be BC, because that's just going to be where they're overlapping each other. And then finally, for this slide, what is ray BA? So starting at B, going in the direction of A, and CD, what is their intersection? Well, they don't intersect. So we would say no, I would say does not exist. So does not exist, which we can shorthand as DNE, does not exist. There is no intersection between these two. There's nowhere where they overlap. So our next geometric object that was defined by Euclid was something called a plane. And he defined a plane as a surface which lies evenly with the straight lines on itself. In other words, a plane has length and width forever, so that it can actually contain lines within it. So planes are two-dimensional surfaces, with infinite length and width, but they have no thickness. So you can kind of see a picture of a plane here in our drawing. So this contains line AB. It can contain a point C, but P is the plane itself, and it's drawn to look like it stops, but it actually doesn't. The plane goes on forever and ever and ever. And so the most famous plane that we have, that everybody learns about in school, is called the Cartesian plane, also known as the XY plane. So this is where we graph things, is in the XY plane. So if this was X and this is Y, this is where we graph stuff. It does say all planes must not all planes must extend infinitely. Sometimes they do have limited area. That's fine. But in the case of like the Cartesian plane, it does extend indefinitely. So two other things, planes can also be parallel or perpendicular or not. And so here's an example of illustrating two parallel planes. You see in 3 dimensions, they are parallel with each other. They're kind of going at they're equal a distance from each other, and they're never going to touch. As we're over here, we're trying to illustrate that we have some intersection. If the angle between these planes was 90 degrees, then we would say that they're perpendicular. Otherwise, they're just intersecting. Some other interesting notes is something called collinear points and coplanar points. So if I put 2 points on this plane, let's say this is point A and point B, then those are called coplanar because they're on the same plane. All right. But if I put B down here on the second plane, then they are no longer coplanar, they're non-coplanar. All right. You can also have collinear. So if you have 2 points, let's say point A and point B, and let's just make another point over here in the space, point C. So A and B are collinear. They're on the same line, but C and A, or C and B, are not collinear. They are not on the same line. So C is not collinear, A and B are collinear, so we say C is non-collinear. And then if they're on the same plane, they're coplanar. So that's just some definitions over here. So to look at that over here, let's say this was point E, and over here in this other little space, that's F, and then let's say we had one here, that's G. So E and F are coplanar. They're on that same kind of light beige colored plane, and then G over here on the blue is on a different plane. It's on this blue plane, this light blue plane, and so G is not coplanar with E and F. E and F are coplanar with each other. So let's just review from, back in the day, how to identify places and points on a graph and then use that information to describe. Because one of the beautiful things about the Cartesian plane is that it allows us to do some really, really advanced cool math with geometry, which was, kind of the cool part about it. So identify the location of points A, B, C, and D. So again, this is the X plane and the Y plane. So we call this the X and Y plane, or the Cartesian plane. To review with you, it's broken up into quadrants. So quadrants go in counterclockwise order, starting with the first quadrant. This is the second quadrant. This is the third quadrant. And this is the fourth quadrant. And so that's how we kind of identify where things are in the Cartesian plane, is based on what quadrant they're in. So in the first quadrant, everything is positive. So your X and Y values are positive because you go right and then up. If you go left, that's negative. So going left is going in the minus direction, and then again going up is positive. So all the values over here are going to have a negative X and a positive Y. And then going in the third quadrant, you went left and down. So both are going to be negative. Your X and Y's will be negative. And then in the fourth quadrant, you went to the right. So that's positive, but you went down and that's negative. And so that is how these numbers work. So for example, point A here is going to be at the point 4, 3. And so that is its location in the Cartesian plane. And point D here, we'll just do D because it's also in the first quadrant, is going to be at the point 1, 1. Now over here, point B is in the second quadrant, so its X value is going to be negative. It's negative 4, and its Y value is 1 because it went up 1 in the Y direction. And then over here at C, it went left 2, so it's minus 2. And then it went down 3, so minus 3. And there you can see how that works. Things in the first quadrant are all positive. If you're in the second quadrant, your X is negative, but your Y is positive. If you're in the third quadrant, both of your coordinates are negative. And then there wasn't anything in the fourth quadrant, so we didn't have to identify that. But we would have seen that an X is positive and the Y is negative. So number 2 says describe the line from point A to point D. And so from point A to point D, we would just say that that's a line going from the point 1, 1 to the point 4, 3. And so that would be AD, would just be the going from the point 1, 1 to point 4, 3. That's really all the description we really need to talk about. It just allows us to give us coordinates. And then describe the line from C to D. So C to D. There isn't really a given line from C to D. But if we were to describe the line, if we were to make a line there, then we would say that that line would go from the point -2, -3 to the point 1, 1. But there isn't an actually drawn line there. So, and then does this figure represent a plane? And the answer is yes, this is absolutely a plane. It has two dimensions. It has length and it has width, but it doesn't have any depth, and it contains lines, which is one of the purposes of a plane. So it's kind of the idea behind a plane. All right, so that's the end of this section's video. If you haven't done so, go on over and read section 10.1, points, lines, and planes in the textbook. Once you've done that, remember there are problems at the end of the section, within the section called Your Turn Problems. I would advise you to work on those and practice to see if you really understand what's talked about not only in the textbook but also in this video, and complete the associated homework assignment for this section in the LMS. And if you have any questions, feel free to reach out.